Hey chemists, welcome to the Classifying Chemical Reactions lab. In today's lab, we're going to be seeing a bunch of different types of chemical reactions. Now we've talked all about chemical reactions. We know that in a chemical reaction, we have reactants and products. The reactants change into the products through a process known as a chemical change. And we know that there are a bunch of different indicators of a chemical change, signs that a chemical change is going on and that something new is being created. We've talked all about the different signs or indicators of chemical change. We know there's an unexpected color change, there's the formation of gas or bubbles, the formation of a precipitate, a new odor or smell, and even the release of heat or light as energy. So we know how to recognize a chemical equation, and we know a little bit about how chemical equations should look. But did you know that there are different types of chemical reactions? Just like there are different types of Pokemon. Yeah, I had to make a Pokemon reference. They're all different types of chemical reactions, and we're going to work on identifying them today and talking about what's special and unique about each of them. Okay, so for our first type of reaction today, we're going to be talking about a combination reaction. So in a combination reaction, you should be able to figure out what happens. We have two separate chemicals and they're going to combine. So in a combination reaction, we start with two separate elements all by themselves. And they're going to end up combining together into something new, into a new chemical that has all the elements on the reactant side too, but combined together in a compound. The formula for this is A plus B yields AB. Okay, so for my first reaction, my combination reaction, we're going to be burning one of our favorite elements, magnesium. We've seen magnesium before. It's a silver gray strip that looks like a very, very shiny metal. So this magnesium metal is starting off silvery and shiny. It looks a little bit white in the camera, but it's pretty silvery and gray for the most part. So we're going to be taking this magnesium and burning it. The element we'll be combining it with is oxygen. Anytime you're burning something or combusting something, you're combining it with the oxygen in the air and forming a new substance. So we're going to burn this magnesium here with our Bunsen burner. I'm going to go ahead and light our burner. So we're going to go ahead and light this magnesium on fire. Remember, anytime we're lighting magnesium, you don't want to look at it directly. In the video, it should be okay. But we're going to go ahead and light this up and see if we see any signs of a chemical reaction going on. Okay, so my magnesium definitely reacted there. I had all kinds of signs of a chemical reaction there. I saw a new gas being formed, a lot of heat and light and smoke. And now I want to see if I have a substance that looks different, that might have unexpectedly changed colors. Let's take a look. So here is my product, MgO, magnesium oxide. Does it appear different from what we had before, from that silvery magnesium metal? Go ahead and make some observations about what you see, and then write down the evidence that you saw that told us that we had a reaction. Now think again. What told you that this was a combination reaction? In a combination reaction, remember, we're starting with two separate elements. In this case, magnesium and oxygen. And we end up with a compound on the right side of our equation. So, how can you tell, just from looking at the reaction that we have written up above, that this would be a combination reaction? Go ahead and write your thoughts now. So for our second reaction here, we're going to be looking at a decomposition reaction. You can probably guess what's going to happen in a decomposition reaction if you know what it means to decompose. To decompose means to break down, like fruit might rot and break down into simpler chemicals. Like a log in the forest might rot over time and break down into smaller parts. In a decomposition reaction, we start with one chemical. That's a compound, a combination of two or more elements. And that chemical is going to decompose or break apart into the elements that it's made of by themselves. So it's going to break down from a compound into multiple elements. The format of that is going to be AB, A and B being two different elements combined together, yields A plus B, A and B being two separate elements in this case. So now we're going to take a look at our decomposition reaction. Remember, in decomposition reactions, we're splitting one compound into two different parts. Those parts might be elements by themselves, or they might be other compounds. But we're breaking down one big compound into two smaller ones. So in this reaction, my reactant is something we call copper 2 carbonate, CuCO3. So I'm going to take a look at my copper carbonate, and it should seem familiar. Where have you seen that very pale shade of green before? That's right, you should have seen it on the Statue of Liberty. If you didn't know, the Statue of Liberty was originally made of copper, solid copper, which has that characteristic reddish-brown color and is a shiny metal. Over time, that copper reacted with the chemicals in the air until it formed what we call a patina, that pale green color that we see as copper carbonate. So next time you see the Statue of Liberty, you can think, ah, that's copper carbonate on the outside. So we're going to take this copper carbonate, I'm going to take 2 spoonfuls, spatulafuls, and fill up my test tube here. All right, I'm going to hold my test tube of copper 2 carbonate with a test tube holder. I'm going to light my burner, and then I'm going to heat it for 3 minutes. Decomposition reactions often involve heat, because heat is really good at breaking things down and providing the energy you need to break the bonds in your substance. So I'm going to turn on my Bunsen burner, start heating this up, and wait for 3 minutes. So whatever I have in my test tube is definitely not copper 2 carbonate anymore. You can clearly see that this substance is a color that we didn't see before. You might say there was an unexpected color change. What we have in this test tube is actually copper 2 oxide, this black substance. The other chemical we were supposed to have produced from this reaction was carbon dioxide. Now, carbon dioxide is a gas that's actually heavier than air. It should still be inside this test tube, and if we have carbon dioxide in this test tube, well, then we shouldn't be able to have a fire inside of it. Why is that? Think, what do you need for a fire to stay lit? Oxygen. So we're going to test to see if there's any oxygen in this test tube or if it's all CO2 and if our flame goes out. So I've lit a wooden splint now, and if we stick that wooden splint inside this test tube and it goes out, that proves that we produced carbon dioxide. and you should see it went right out. So, we have a lot of evidence of a chemical reaction here. We have an unexpected color change, and we can tell we formed a new gas in the form of carbon dioxide. So this is a decomposition reaction. Again, what tells you that it's a decomposition reaction? We started with one chemical, and now how many do we have? What happened to my bigger chemical? It broke down into smaller ones. That's a decomposition reaction. For our third type of reaction, we have a single exchange reaction. So, I want you to imagine something with me for a second. I like imagining things. Imagine you go to a dance, but you go all single and alone. You really want to dance with somebody out there, but there's nobody free. Everybody's already partnered up and paired up, and you're all alone. What are you going to do? You're going to cut right in, right? You're a single, suave young teenager, and you know you can dance with anyone that you want to. But you're going to steal somebody's partner and switch places with them. And now, that person is all on their own, by themselves. This is what happens in a single exchange reaction. We have one element, single and by itself, just an element all alone, and a compound, two elements already partnered together. That single element is going to come in and kick one of those elements out of the place of the compound. It's going to form a new compound with the other element that it partnered up with, and that other element is going to be single and all alone. The format of this is A, which is a single element, plus BC, which is a compound of two or more elements, yields AC, the original single element and its new partner, and B, the element that used to be partnered in that compound. So for my single exchange reaction, my two reactants are going to be zinc, a shiny silvery metal, and hydrochloric acid, which looks just like a regular clear liquid like water, but you don't want to treat it like water at all. This is a very corrosive, strong, dangerous acid. That's why whenever I work with hydrochloric acid, I'm going to wear gloves and my goggles at all times. So I have zinc and HCl. Zinc is an element all by itself, but HCl is two elements partnered together in a compound. Remember, in the single exchange reaction, one element is single and all alone, and it's going to want to kick out the happy couple and partner up with one of those elements. So we're going to take my pieces of zinc here, and I'm going to add a couple pieces into my test tube here. Okay, so now I have my zinc in my test tube. I'm going to put it into my test tube rack. And now I'm going to take my hydrochloric acid, 5 milliliters already measured out, and I'm going to add it into the zinc and hold a test tube upside down over that tube. So why do you think I'm holding this test tube inverted over this other test tube? What sign do you have that a chemical reaction is going on right now? It seems like I'm producing what phase of matter? I'm producing a gas, right? So this gas, according to my equation, should be hydrogen gas. And the thing about hydrogen gas is that it's extremely flammable. So we're going to see if I did produce hydrogen gas in this test tube and if I can light it aflame. So let's see if I can light this hydrogen gas up. Did you hear that? Let's try it again. Whew. So if you heard that sound right now, that was the sound of what we call a hydrogen pop test. In a hydrogen pop test, you light the hydrogen gas, which is very flammable, and you hear a very characteristic sound. To imitate, whoop, right? a very, very loud, sharp whistle. That's proving that we produced hydrogen gas. So let's think about what happened here. I had zinc and hydrochloric acid. Hydrogen was all nice and buddied up with chlorine. But somehow we got hydrogen gas, which is H2, all by itself. What did the zinc have to do to kick hydrogen out of that compound? It had to cut in and partner with the chlorine. So at the end of the day, in this reaction, we now have zinc chloride and hydrogen gas. Alright, I want you to imagine another scenario. This time, you go to the dance with somebody that you ask, and your best friend also asks somebody and they have a partner as well. So you go to the dance and you're dancing on the dance floor and you're having an okay time. But really, the person you have a crush on is dancing with your best friend. And the person that they have a crush on is dancing with you. So what are you going to do? The double swap, right? In a double exchange reaction, both chemicals are swapping partners. So you're going to end up dancing with the person that you really want to be with, and your best friend's going to end up dancing with the person that they really want to be with. In a double exchange reaction, my compounds are going to do the same thing. You'll start with two compounds. Each has a partner. Each is paired up in an ionic compound. But those ionic compounds are going to switch places. They're going to swap partners. That's why we call it a double exchange, because two ions are exchanged. So the format of this is AB, two or more elements in a compound, and CD, two or more elements in another compound, yields AD and BC. So they both swap partners and form new compounds, some of which are going to have different properties than our original compounds. So, for my double exchange reaction, now I'm working with two ionic compounds that are both aqueous, dissolved in water. In my two graduated cylinders here, I already have them measured out. I have zinc acetate, ZnC2H3O2, and sodium phosphate, Na3PO4. They're both just clear liquids. I'm going to add them into one of my test tubes here and see if I can observe signs of a chemical reaction. So here's my first clear liquid, zinc acetate. Now I'm going to add the sodium phosphate and see what happens. Watch closely. So you should have noticed a pretty stark change there. I had two clear liquids, and now I have a bright white color. In fact, it even looks kind of like I've got chunks floating around in there. Solid chunks. What do we call that when we mix two liquids together and form a new solid? It looks like snow falling from the sky, which we call precipitation. And that's exactly what this is. This is a precipitate, a solid formed from two liquids. But how do we get this precipitate? So before I had two clear liquids, two compounds that were soluble, able to dissolve in water. How can I tell that I have a new substance here? Well, that new substance is the precipitate. That solid is no longer able to dissolve in water, and so it comes out. It falls out of the solution and falls to the bottom of my test tube. That precipitate is Zn3PO42. The zinc that used to be with acetate has switched places with sodium, and now it's with phosphate in the form of a solid. That's a double exchange reaction. Two ionic compounds swapping partners to form a new compound, usually in the form of a solid precipitate. So that's all the time we have for today. You just saw 4 different types of reactions: the combination reaction, the decomposition reaction, the single exchange reaction, and the double exchange reaction. Now you're going to take some time to look at some chemical equations and start classifying them on your own. You're going to look and see what parts you see in the reaction. Do you see 2 elements combining to form a compound? A plus B yields AB. Do you see 1 compound breaking down into 2 smaller parts, either elements or compounds? AB yielding A plus B. Do you see a single element and a compound, and that single element comes along and kicks out one of those elements, takes its place, and makes that other element single? Or do you have 2 compounds that both swap partners? Using that knowledge, you're going to go ahead and classify some of your reactions on the last page of this lab and practice balancing them as well. Thanks for being here, guys. Thanks for watching, and we'll see you on the next one. Stay curious, chemists. Wait. I'd be remiss. I'd really regret if we never actually got to talk about my favorite kind of reaction. Now, my favorite kind of reaction isn't one we classify or talk about in this course, but I gotta show you. So let me demonstrate real quick for you guys what a combustion reaction looks like. A combustion reaction is different from all the other reactions we've talked about so far, because we don't just have random parts, we have specific elements in this reaction. A combustion reaction always starts with an organic compound that contains some amount of carbon, hydrogen, oxygen, maybe nitrogen, things like carbohydrates, waxes, alcohols, wood. Any of these kinds of substances will burn in the presence of oxygen. So we're going to combine that organic compound with oxygen. And when we do, we're going to get 2 gases from it: carbon dioxide and water as a vapor. So we're going to check out one of those combustion reactions here. It's one of my personal favorites called the whoosh bottle. So go ahead and just enjoy with me here our demonstration of a combustion reaction, the whoosh bottle. Okay, so for my combustion reaction, I have a chemical known as methanol, also known as methyl alcohol or wood alcohol. An alcohol is actually just a type of organic compound with carbon, hydrogen, and oxygen in it. There are actually a bunch of different types of alcohols, like wood alcohol, grain alcohol, isopropyl alcohol, even tert-butyl alcohol, which we saw in the physical and chemical changes lab melt in my hands. So we're going to pour this alcohol into my whoosh bottle here. And what I'm going to do is I'm going to swirl it up and coat the walls of this bottle. One thing about alcohols and a lot of organic compounds is that it's very volatile. In other words, it transforms into a vapor or a gas very, very easily. So when I do this, when I coat these walls of this whoosh bottle with the methanol, what I'm doing is I'm filling up the space inside of my bottle with vapor, methanol vapor, which just happens to be very flammable and ripe for a combustion reaction. So I'm going to swirl this up. I could even hear the vapor escape there at the end. And I'm going to go turn off the lights and then light this whoosh bottle from a safe distance. So there you have it, our final type of reaction, the combustion reaction. We can clearly see that this methanol here, combined with the oxygen in the air, produced a good bit of light and heat and formed some new gases, carbon dioxide and water, inside of this bottle. Now here's the thing, I'd love to do that again, but I can't, because this bottle here is now full of carbon dioxide and water. Ah well, Some reactions in chemistry can be short-lived, but we'll always remember them. That's really it this time, guys. I hope you enjoyed our Classifying Chemical Reactions lab, and we'll see you on the next one. Stay curious, chemists.